Hello everybody, my name is Artun Sevgili and I'm going to be presenting you my EEE474 project, which is magnetization transfer in MRI. So I'll start with the background information. So there are two types of protons in living matter. So first one is the one you can find in water, which is mobile protons. I'll be calling them free protons because they're not bounded to anything. So these protons have a very narrow resonance length, which we exploit in MRI scanning, and they are directly visible in MRI because of their very long decay period. So it takes a very long time for them to decay, so we can image them much easier. So they're directly visible in MRI because of that. And unlike these free protons, there are protons that are bounded to macromolecular structures such as proteins and lipids, and also cell membranes. So they are much less mobile than these free protons, which we call them, because of that reason, bounded protons. And they have a much broader resonance line, which I'll show you in the next slide. And they are not directly visible in MRI because of their very fast decay speeds. Our aim in magnetization transfer imaging is we want to be able to find the locations of these macromolecular regions, where they're located, so we can analyze them. But they're not directly visible in MRI, so that's a problem. So we are going to exploit the properties or the effect of magnetization transfer in order to see their locations. Here we see a picture of the bounded protons and free protons. You can see there's a huge structure over there, a huge compound, which is, let's say, a protein, and a proton, which is represented by the hydrogen atom, is connected to it, and adjacent to that is the free proton in water. And in the right picture there, you can see the line shapes of both of these pools, the liquid pool, which is the free water pool, as a very sharp resonance line. As you can see, it's almost only response to RF pulses in the resonance, and unlike the free water resonance line shape, uh, molecular pool has a much broader line shape, which, as you can see, it responds to off resonance pulses as well. So our strategy for imaging these macromolecular pools will be, we're going to be sending a RF saturation pulse off resonant from the laminar frequency, and since the liquid pool has a very sharp resonance line shape, it will not be affecting the liquid pool, but it will affect the macromolecular pool. So we will be able to selectively get a reaction out of these macromolecular pools, and through the use of magnetization transfer, we will be able to see the effect in the final image, which I'll get into and explain more elaborately in the preceding slides. So this is the two-pool model used in explaining the magnetization transfer effect. So pool A and B represents the free water and bounded pool respectively. And what happens here is the shaded region represents the saturated spins. So as we expect, the saturation after excitation decays with T1. And since the bounded pool saturation decays much faster, so fast that we can't scan them, we would ideally want the bounded pool to transfer its magnetization over to the free water pool, so that because of the much longer decay periods of the free water, we will be able to scan them using the magnetization transfer. So to repeat that once again, we will, using an off resonance saturation pulse, saturate the bounded pool, and they would ideally transfer their magnetization over to the free pool, so that the magnetization would last, and we would be able to see the effect of the magnetization when we scan them, because of the longer decay period. So I think this picture summarizes and explains it much better. So the longitudinal magnetization MZ it starts as M0, the equilibrium magnetization, and when we send the RF off resonance RF pulse, there will be some direct magnetization to the liquid pool, but we would ideally ignore it because we should calibrate the off resonance so that we have a minimal effect on the liquid pool itself directly. And the main decay in the magnet, or let me not say decay, but main degradation in the magnetization will come from the transferred magnetization coming from the bounded pool. So it is indicated by MMT, as you can see. The magnetization is transferred so that we the liquid pool gains saturation, so MZ drops by MMT once again after the direct magnetization. So we have a much lesser longitudinal magnetization coming into a gradient echo pulse or any other imaging scan method you may like. So our initial off resonance RF pulse degrades the MMZ so that there is an effect corresponding to amount of magnetization transferred, which is location dependent, so that we can locate the locate the regions of most magnetization transfer, which will give us, of course, the regions of macromolecular compounds. So to quantize this effect, we can see the magnetization transfer ratio, which is given as M0 minus MZ over M0, which to put it verbally, it gives us how much degradation we're experiencing compared to the equilibrium magnetization. So I think if I give some examples, it will be much better for us to visualize it. So in the figure 4, there are two pictures of a brain, and the first picture, actually, there's no MT pulse or off resonance pulse. Magnetization transfer pulse, short for MT, is what I'm going to be referring to, the off resonance MT pulse. So there's no MT pulse, as I said, in the first picture, which shows just a bare image, and the second picture here is the image sequence with the MT pulse. So as you can see, there's a degradation in the overall signal, and the white lines outlined and the crevices here indicated by the arrows, they show the sources of MT, which is the macromolecular regions. As I said, those white light outlines show the regions of macromolecular content that we are trying to see in magnetization transfer contrast. And another example is figure 5. Here we can see the arteries, and one taken without MT pulse, as you can see, has much less arteries showing, smaller arteries showing in the first picture, but in the second picture with the MT pulse, there are these smaller arteries which are not previously visible. So as you can see, we are taking advantage of the magnetization transfer to be able to see these smaller details. So coming to our imaging sequence, I'll be using a spoiled flash fast low angle shots with off resonance MT pulse. As you can see, my off resonance MT pulse is a Gaussian pulse, so this is because I'm trying to avoid SIR limitations, as a Gaussian pulse has better SIR specs for me, and some power amplifier, RF power amplifier limitations as well. You could use technically any other pulse, sync, or etc. But this is what I use for the limitations of my specific hardware problems, and the rest of the imaging sequence is very traditional low angle shot imaging with spoilers, and we're going to be using a sequence and taking an image with an MT pulse and one without, as just as the examples I've showed you. And to calculate the MTR, we're going to be doing the we're going to be applying the equation or the formula I showed you, just dividing and subtracting the images. So as you can see, all of the other specs or criteria or parameters of the sequence is kept the same from the one with MT and one without. Just the only difference is we are omitting the MT pulse in one case. And these are the results, these are the images. I imaged a piece of meat, and as you can see, it has some bones and meat, And the one I'm trying to focus on is the regions of macromolecular content. So in this case, the region of most macromolecular content is the cartilages and the tendons of the bone. So the red arrows indicate those areas. As you can see, the top of the bone has some cartilages, and as expected, the tendons are along the side of the bone, and some other content is highlighted by the red arrows, the regions of most macromolecular content that we can see by observing the image. The tendons and cartilages are expected to be in the locations indicated by the arrows, so we can see the effect of MT very clearly. So the MTR map is drawn and shown as indicated in the figure. The regions of most macromolecular content and most MT transfer is aligns with this image. So um, there's some noise, but when you look at the outline of the bone, etc., you can see the places or regions where the MT transfer took place the most. So we can quantify how much MT transfer happens in what area by looking or observing this MTR map. So some possible improvements are testing the offset frequency. For example, my offset frequency was 1K, which was standard for this operation as I researched, and some different shapes can be tested for MT pulses. For example, as I said, I used a Gaussian pulse, but you can use a sync or rectangular and see what you get and how different the results were. And as I said, for me, the SIR and power amplifier problems were important things. So I ran those hardware problems, but um, if you didn't, you can try these sync and rectangular pulses to see how those improve your results, basically. So these are my references I used to conduct this project, and thank you for listening.